So now I will switch to English. And so thank you very much for coming. And so in these two talks, my plan is give a sketch of actually work in progress joined with Renato Betiol from CUNY, where we implement the bifurcation method in a special class of manifolds called cohomogeneity 1 manifolds. So my plan explain all these names and in these two talks. All right. So first of all, let me what do you want to say about Serrin problem, the Serrin problem. In our case, this is a specific problem for us. So we consider one manifold, and you can imagine it is complete oriented connected with one. And so an omega will be a bounded domain with a smooth boundary. And the second problem is this specific problem. So we are talking about this equation in omega, and with these two conditions on the boundary. So this is the Serrin problem, as you, of course, well know. This specific problem has a lot of motivations, right? And I will skip this part. It's pretty classical. Gracias. Okay, and it's called Serrin problem because it was first studied by Serrin, J. Serrin. Okay. The case of the Euclidean space, right? I mean, so we know that if omega, our manifold is the Euclidean space, and this domain admits a solution to this problem, then omega is a okay. Well, in the paper itself of Serrin, you'll find many applications, but you can see other papers like the papers of Piraberto and also the thesis of Jean Wang last year here. So there's a lot of motivations. And my first remark, it's important. Serrin also proved the same result for a more general equation, as you know. The same paper, actually. But it is also true for the more general equation. With the same boundary conditions, okay? And of course, I forgot to say that this is an over-determinate problem because I have two conditions on the boundary. We always have, for every bounded domain, we always have a solution if you, for example, consider the Dirichlet problem. And so when we impose another condition, this is actually a problem about the domain, right? Including, of course, another remark, very basic remark. This constant here is not, I mean, this is determinate, right? So we can integrate the equation and see that, so of course, by the maximum principle, it's negative, but if you integrate here, and you can see that C is in fact minus the volume of the domain over the volume of the domain. So, I mean, the constant is also geometric. All right. Another, and maybe here. Okay. I'd like to say this is also true the case of domains in the hyperbound space or in the sphere. All right. This was proved by Cavalcante. Or even in the, so there, of course, you know, this Serrin applied the moving plane method, and it also works in this setting. But it's very interesting, I'd like to mention also, this is also true in the whole sphere if the domain is a disk, like the Hop theorem, as proved by Jose Maria and Mohammed there. I forgot the name. Okay. Sorry. Okay. Okay, so I'd like to talk first about some basic examples. So, starting from this point here, and of course using like a product structure, we can construct, yes?
This is true for positive.
Oh, sorry, thank you. Sure, of course, in the general case, you can. Sorry. So my point is to deal with this problem in manifolds, in many manifolds. Okay, and so I'd like to talk some basic examples, which are, of course, the first one will be the ball of radius r, okay, in the Euclidean space, and so the solution is basically. And so from this first basic example, we can construct other ones like I will call CR, which is VR times the cycle, right? So my manifold here will be the Euclidean space. This one, and then we have a solution if you consider in this product structure function depend on this solution here. All right. So then you can see that there's a solution in this cylinder, right? And of course, the same if you take the universal over here, okay, we call CR tilde will be VR times but this is an unbounded domain, a cylinder, right? And of course, you see why these guys are important. 1 second. Right. And You can do the same of example B in if you change n by the hyperbolic space of the hemisphere. You take the solution, the geodesic ball in this case, and then take the product by S1. All right. Okay. So now, example C, I'll call AR, which is an annulus in the sphere. Right. So this is the equator, and then you take the annulus of distance r to the equator. So this guy would be always in the sphere such that the distance to this point for the equator I will call not like this. Okay? And so this guy is an r. This is my domain. And yeah, we can solve the problem. It's in this case, we consider the functions depending on the distance. And this is an ODE, all right? So the solution, I'll call this guy T, all right? And then the solution, we'll call denoted by this guy. This real function depends on the distance. So we can see that in this case, the problem, when you put in the coordinates, you find this ODE here. And I mean, the boundary conditions to this ODE is so in R is 0, and since it's a smooth function, the derivative here is 0. And for example, if n, I hope I'm not wrong, yes, dimension 3, you can see, you can find the solution in each dimension, but I don't find a general formula. But in dimension 2 is quite simple. It is cos 2t over 4 minus cos. So this is the constant. Explicitly. Actually, this is one of the main points of tracking this problem, because in general, you find a split solution to this problem. It's quite different from the problem about the eigenvalue problem, for example, extremal domains. It's quite hard to find a split solution, which is not the case. In general, for Serrin problem, you can find split solutions, right? I'm sorry, I have a lot of examples. Only more 2 examples. So I'm trying to be fast. So this is, you take the sphere times an integral, right? So this is a subset of this product. And in this case, you can take the one-dimensional solution here. It means so this is the solution of the space in dimension 1. Of course, we can do the same. I mean, in general case, I'll skip this. And the last example, maybe more interesting. We'll have the 3 sphere, and you consider the domain such that the boundary will be, I'll denote by sigma r, which is this CMC torus, right? The family of Clifford torus. Note that you have 2 domains with this property, right? So this surface bounds 2 domains, and you can choose any one. In this case, again, so I will denote by sigma 0, this geodesic here. Okay, so I will consider, I'm sorry, but I say that, well, consider this guy in two times, right? And so take omega. So this is the geodesic. Okay, and again, if I denote by t the distance to this geodesic, you can see the solution. We have the equation, but let me put here the solution of the ODE is all right. So and is it, and finally, maybe an example, we will more or less the general case. Okay, so it's not example actually, but if have a subgroup of isometries, of course, should be at least dimension 1. And omega is G invariant. Then omega limited solution. Then the solution to the Dirichlet problem is also a solution to the Serrin problem. I mean, the normal derivative is constant along the boundary. So then this is almost a remark. The solution U is right. So every domain in a Riemann manifold, which is invariant by a subgroup of isometries. At least, at least
cannot split.
Sorry.
It cannot be discrete.
So
No, of course not.
the
I mean, yeah,
boundary,
compact.
the
not
boundary
discrete.
is G homogeneous, no? G acts on the boundary in a homogeneous.
Right, also, sure, yes. Same way, to have this condition, right? Right. And so this is the case in our example, right? I'll explain 1 minute. And it's important remark. The same is true. This is interesting. Of 204 external domains. It's when we consider the first integral equation, we know that I mean the same. Okay. The point is the solutions, they are not explicitly anymore. Okay. And now I'll talk about new examples just briefly. What I will say right now is after a work of Cavalcante, 2010, Cavalcante wrote the first paper where he used this theory of bifurcation to construct new domains, all right, satisfying the support and solution to this problem here. Okay, let me call 2. So Robert found first examples of domains, external domains, bifurcation, the family CR, right? So
Excuse me.
yes,
In RNHA, the serine serum holds, but in SA, the serine serum doesn't hold. So here is current example. Yeah. The serine serum doesn't hold in SA.
the serine.
Yeah, the serine.
Now you have domains that are on bonds.
Yeah, this is the current example.
I mean, more or less, yeah.
Yeah. Could you give some remarks why the serine serum holds in RNA and HA but doesn't hold on SA?
I don't know if I understand well, but I mean,
Because the technique doesn't work.
You wrote there that the steering fuel also hold in S2.
Oh, yeah,
This is not true, in fact, because such domain exists in S2. But what the Spinel must prove is that if the topology of this, then it is a ball.
right. Sorry. Thank you. Yeah,
Is that the analogy with minimal surface is that you can have for example, chloride in a sphere that you can have in the plane space, or you can have spheres, minimal spheres in a solid that you can have in the. That's the analogy.
And in fact, even with the topology of a pole, if the equation is different, it's not true.
you are right.
So in fact, there we needed 2 hypotheses more, that the equation is Laplacian u plus 1 equals 0, and also that the topology of omega is this, right?
Yeah, it's controlled.
Your result is this one.
Oh, right. I'm sorry. Right. I mean, yes, I remember the paper of Jose and Lohan. There's a hypothesis on the nonlinearity.
Yeah, it's
So
the
there's
F have to satisfy.
Yes,
You're right. Thank you. Right. Right.
and the topology also.
Yes, the topology and yes, I'm saying this problem here, but so if omega is a this topology and the nonlinearity is bigger than a constant times.
So in particular for Serrin and for the Ivan problem, exactly. It's not exactly that for those kind of works, but it's more general.
But then in the general case, if you have no this hypothesis, then you have counterexamples.
So also in the case of f equal to 1,
You can solve it.
you can use.
Yeah, it's not that condition. It's
not
not
that
that
condition.
it's not that condition.
Everything was?
Yeah,
That
fine.
zero is something that is, yes. Yeah, this is 1.
So quickly here, I follow different examples. And, first of all, as I said, Cavalcante and Cavalcante. So they found new examples bifurcating from these cylinders, right, for the first eigenvalue equations. So I will just draw a picture. Okay, so we can, of course, it's interesting because, so, for example, if the radius is less than p, I guess, or p over 2, you can assume that this wall is inside a square, a cube, such a way that you can consider those domains, CR, as a subset of the torus. So this guy, if it is small, is inside the torus, and then they perform. So the R is radio here. They can perform found new solutions, something like that, right? So you can consider this guy in T and one, for example. So this is very important because first they found the counterexamples for the Beresik BCN, Beresik Farelli-Nirenberg conjecture, the first examples, and also started applying this method. After that, they opened the door. They have today a lot of papers, and so I'm trying to enter in this field essentially. And okay, so I'll try to skip you. Maybe you know very well this. So the first paper they found a discrete family, and here's a continuous family, depending on the kind of bifurcation that you apply. Okay, let's see. And okay, so I will skip some. I mean, just saying that then we have a paper from Moravito. At least, you know, in the journal is the second one. They say for the same family, this family here, but if you change the space by the Hackman space, I mean, the same found new examples. Okay, I'm talking about new examples from bifurcation. So they did this in geodesic ball times essentially S1. And then yes. Let me call a Serrin domain is a domain supporting solution to the Serrin problem. So found Serrin is bifurcated from this family here, essentially, all right, because they also consider high dimension is the same idea, essentially from this family. And also for this family here in the sphere, 2 years later. Okay, so they take this and they apply the method and found no new domains looking like that. So if you take from the family AR, the over there. All right. And recently, Filippo saying from the family TR, right? So some, in this case, more so take these steps to find out. What else like that? Well, there are a lot of other papers and other equations, but I like to mention this kind because we try to put all these, at least for the Serrin problem, we are trying to put all these examples in a unified setting. That's the idea. All right. So now, what is it? I'll talk about cohomogeneity one manifolds. Okay, I have time, right? And yeah, I'll try to talk now about cohomogeneity one. What is it? Actually, essentially, as in this case here, right? So we consider, as before, compactly grouped, non-split, acting. So group of isometry, so acting by isometers. But such that is the condition the orbit space is dimension 1, right? So this is the definition. But we consider a special case where this is an interval of this called I. So the condition is, I will explain what I mean. So this is an interval of this type. Right, like that. But this guy could be sometimes as infinity. All right.
An interval or is one?
Is an interval. So it's an open interval. If I mean it's the half-life or a closed interval. I will show some examples. Yes. Okay. Let's see if it works. So, yeah. Okay. So I added some notation. So denote by the quotient map. And fix consider geodesic, right? Parameterized by this interval. Maybe in the open. Um, such that and so we denote by sigma t in case of sigma t in this hypersurface. Okay, so this and so this is we call this principal orbit. This is one. And sigma 0, right? So the pre-image of 0 and sigma L are non-principal. Sometimes, I mean, in general, when the dimension is strictly less than n-1, we call a singular orbit. Well, interesting thing is, okay, no problem. I'll draw everything again. So, first remark in this setting is sigma 0 and sigma L, right? Because finite are always minimal coordinates. Right, made a point, okay? If you consider as a geometric. Okay. Again, if t is in the open interval, we denote by g gamma t the principal isotropic group, which is the stabilizer of this point. Okay. Principal isotropy they are all isometric, I mean, homeomorphic, and we denote this guy by H. Okay, so this is a subgroup of G, and we denote by K. The same for this guy, and okay, I don't need the other one. So H actually is a subgroup of K, which is a subgroup of G. Okay. Moreover, from the theory, you can see, not hard to see that sigma is, I mean, the principal orbit is always diffeomorphic to this instance, and the sigma 0 is okay. All right. And now the examples, finally. So, in the space, the group we consider they are the SON. And so the parameter space is the half-line. The principal orbits are the hyperspheres. Okay, so these are the hypersurface which are fixed by this group, and sigma 0 is only the origin. Okay, and so H, if you wish, is SON plus 1, and K is everything. You can check this property here. Okay. I think I'd like to mention more or less these examples here. At least 3, I guess. Yes, I have only 3 examples, okay? The second one will be A, B. Again, consider the sphere, and we can consider the sphere in n times R, and take this group, so SON times Z2, and where Z2 is almost acting by multiplication on this factor, right? So SON acts here, and the second part will only have a reflection. Okay, so this is a group acting here, and well, this is an interesting example because well, the quotient this is this integral. If you wish, you can consider, I don't know, and V is a fixed vector equator, which is this guy. And so now think a little bit, you see that the invariant hypersurface by this group have 2 complements. They are these two spheres. Okay, in this notation will be the sphere here, okay, of radius, in this case, cos t times 2 cops. So it is, all right, and well, sigma 0 is interesting. Yes, sigma 0 is the equator. Yeah. And well, we have the groups if you wish. The group H is SON minus 1 times 1, and the K is as everything is G. No, is SON minus 1 times the 2. Yeah. Okay, and you can see that goes again. And finally, the last example will be in F3. So what's the point here, right? I will try to explain to you that you cannot perform bifurcation in this example for a problem. We can do here that was done, yes, in here was done by Fall, Milan, and West. And at least in S3, it's a new, result, right? So, this guy, so G, so consider again, right? In this case, and then, so G. Right, so this is the group that makes the torus variant. Okay. So the quotient is the same interval. Right. So this guy. And the group here is only the identity. Okay, sigma 0 is this geodesic and K is 0 times. Okay, and we also can deal with this example in higher dimensions. All right. So essentially, we split the Euclidean space in 2 parts and take the SOK times SON minus K. So you have the other. You can find the torus, the product of spheres, in dimension K and n minus K minus 1. Right. But this guy is important. Okay.
Sorry, man.
Yeah.
About the examples, an example of cohomogeneity one manifold can be a model manifold, which is the product, the working product of an interval with the sphere, for example.
Right.
Because this is the leaves are isometries, no? The group would
Right.
be SO.
I think yeah, that's essentially what I explained right now. There is a result. Sorry, I forgot to say that there is a very important difference. Okay, I'll put here. So there is a book, right? Which it's all 2015, I guess. Lee Springer about isometric actions and the groups. Well, a lot of things, but in particular they deal about the cohomogeneity one manifolds. And so we will have all these results from the data. This is my reference, my phone. Well, okay. Yes, in particular, we have a theorem about the structure in this case. So we denote the NPR. It is the set of points in principal orbits, which is dimension less sigma 0, all right? If L is plus infinity, and dimension less sigma 0 and sigma L. In our case, okay? If L is right? And the point is, well, it's up to you, but the point is, this subset of M in this case can be split essentially as a product via the interval. So there is a map I call phi is very important, which is the interval, right? It's exactly the same interval time is manifold here, which is the show off to sigma t in the principal part. So this is a diffusion, all right, such that so for example, pi of phi of tx is just t, for example. And so in fact, I forgot to say that by construction, I forgot to say here from this equation, okay, we have that actually phi of x is the distance in n from x to sigma 0, and so by this is a G equivariant map, all right? So the group also acts here in this point, acting here, and the essentially commutative phi. And so sigma t, our principal works, they correspond to the image of t, all right? Okay, so for example, we can see, for example, this is polar coordinates in the Euclidean space. All right. For example, so the point is we have this simple, at least for this part of the manifold, we remove two orbits, submanifolds, and then the result is a quite simple manifold domain of space. And so, moreover, I put here because it's important. The map here, can put back the map, original map G. This is just DT2 plus a family of maps depending on T. In other words, this space with this map is iso map sigma t. Okay. And now again examples. Only three, okay? These three examples again. So in the first case, so now we are here. Okay, so between the space and the set. So all principal ones are spheres. So and the map, well, if you wish, you take off the origin. So this is just down, and the the metric here is the Euclidean metric. Is this plus the standard metric sphere. Well, right. And a second example is the sphere, remember? And well, I mean, we can do that. It's quite, you know, have two components. The outer space is disconnected. So I like to skip this, but that's it. This is so we have here two times so Sn plus I will write for simplicity. So this is the equator, and this guy, they are the north and south poles. So anyway, can use the geodesic to construct this map, and at the end, when you can pull back. Okay, so this is quite. And here you have the metric in this guy. And finally, in S3, and this is so sigma 0 is one geodesic, sigma pi is another one. All right. And you remove this, have this split and the map. I mean, the map is split in the so consider the x the x2 the metric in this side. Okay, so this is our set. Important remark is that as you can see, the mean curvature of the principal arcs, they are constant depending on t. Okay, so denote by it's important because I have some signs that mean so second number for minus g so this is we have a minus here also. So okay, so this guy is pointing inside. So this is the direction of pi, right? H. Now this talk will be just the trace. Okay, not normal line. Samples. A. Example A is in the Euclidean space. This is this guy. B. So this is connected spheres. Okay, using our notation, H is minus. Yes. The tangent. And in this case here, okay, the torus H minus and now something interesting occurred. About the time. Any questions?
No, and in the example B, it should be a dimensional constant.
Oh, sorry. Thank you very much. Yeah, exactly. Thank you. If I read the notes. Right. Thank you. Please, again, I mean, you're already, feel free, but again, feel free to interrupt me if you have any questions. And now it's interesting, we need a result, I will call proposition, okay, because it's only a proposition in the paper of Mazepka. We can do 2005. As I said, we know that what happened here, what happens, the non-principal of sigma 0 is always a minimal submanifold, right? And I forgot to say that, and the principal orbit is actually a sphere bundle over sigma 0. All right. So we have always the sigma 0 here, and this, I mean, this is a theorem in the book of Alexandrine and Bethiol. So the principal orbit is a bundle of if the fibers are spheres of the coordination, all right? So if the dimension is D and he is n minus 1, the fibers are spheres of the difference. Okay, and so in particular, there are tubes along this submanifold, and in this case, when this guy here is minimal, we have the mean character of the tube is exactly over T plus O. And you can check, this is the case. Right? So look at, for example, in the first example, the sigma 0 is a point, so this is 0, all right, and I know this. And in the sphere, sigma 0 is a totally Jadesco equator, okay? And yes, I mean, you can see that property. And again, in the case of F3, okay, and we have this behavior always, all right? Okay. And so, well, I'm not a specialist in bifurcation theory, but the main idea, what's the main idea? I mean, let's start think about using this setting to apply the idea of bifurcation. So the idea, as you may know, you have a space, here is a blank space, right? And the idea is to have a trivial solution. And you try to find, okay, it should be a curve, but you can have parameterized like that. And then, at least at some point, you try to find a new solution. And then you can see in this case, if you have a map, I call that. Essentially what we need is, so if you take a function here, you have, this map depends on a real parameter, right? Like R, and a function in this space. We need to compute the derivative in this direction. It's the first step, okay? And then I will try to put our setup in order to find what we have, what we need, okay? What is F essentially in this case? Also like to say that we are trying to put all together in this unified setting, but it is, I mean, the paper, especially the paper of Roberto and this paper of Fall, Milenda, and West, you know, they are the main inspirations. They're just following the same ideas in the more general setting. Okay. Well, just say something. The idea, again, if you have maybe a round domain, okay, a symmetric domain, like you have a lot, okay, admitting solutions. The idea is to perturb, but in a very smart way. And after this perturbation, we solve the Dirichlet problem, look for for example, the normal derivative along the boundary, and try to find a P satisfy the condition. All right? Right. Okay. And the point is how to make, first point, how to make this perturbation. We do that by a graph, but how? Using this simple structure, you know, this product structure. That's the first point. And that was actually made in all the papers, you know, the examples. So I call this section bifurcation setup. Try to implement this more or less like this. Okay, I will talk tomorrow. Okay, okay. So, take a number, okay, and then we denote by omega r. This omega. What is it? Okay, this guy is, for example, the ball in the Euclidean space. Will be the animals in the sphere, and will be the solid torus in the S3, for example. Okay, so yeah. So the boundary, so sigma 0, right? You can see is inside this domain, and the boundary is this principal word sigma r. So the first remark we call proposition. Essentially, I claimed before, but in this guy here, of course, by construction, this is J invariant. So we always have a solution, okay, to the Serrin problem. The Dirichlet solution has constant normal derivative. And but I need an equation. So only there's a unit solution. Okay. Remember the first problem? In this domain, and this is one dimensional, so it depends on the distance. Okay. Where, so in the general case, what we have is when you compute the Laplacian and use our structure, the mean curvature of the principal appears, not really. Right? And of course, this Dirichlet condition. And since we assume this is a smooth solution, the wrong method this is smooth on sigma 0, it implies that it's I prime is 0. Okay? And of course, and the normal derivative along the boundary is on this. Okay, this domain. And now I have a method side. Actually, two. First, we prove that we can prove that this solution okay, and at least we use this information to get this result. The point is, essentially, it looks like this. This is R, this is R of T, this is T. Okay, and now is
So you can do using moving plane more or less.
maybe, yeah, sure. Thank you. Right. Okay. Yes. Because the solution is positive,
One dimension.
right? Thank you. Inside. And the maximum principle is positive, and then okay. Now let's see how can we return okay the domain. Now we take a function phi in this space is most and small. is to 0. All right. Then we denote by dr first. Dr will be only and dr plus 5 will be the points of tx, okay, in 0 L times such that t is less than bigger than 0, of course, than 0. So this is the graph calculation of the cylinder. Okay, so we are here. So this is 0. Somehow this is r, and then so the base is this space. The function is defined, and here is small. So it is okay. So if it is small, let me say sigma t are embedded manifolds. So if it's small, this is also embedded surface. Okay, the boundary here. Is it clear? So have a point x, and this is phi of x, and I'm asking that t is less than that.
T is less than R plus 5.
Oh, sorry. Thank you. Pay attention, right? Thank you. Right. Thank you so much. Thank you. Okay. All right. And then they use this map here to construct the corresponding perturbation in the manifold. That's the idea. And so we denote by omega. Well, the notations, they are a little bit more complicated, you see. This guy will be, I just erased the, so remember we have big 5, and then you take the image of big 5, the image of this domain, okay, and then we will see this. Okay, so this is our domain, the perturbation using this structure. Well, always in the paper, at least once I read, we need a common domain to deal with the bifurcation, okay, a common setting. And then we do this, so we can change the map and consider the map C. You know, sometimes it's plus, sometimes a common. I'm sorry, but this map is defined in D1. Okay, and in this guy here, right? Can be done as so. It is just S minus X. Okay, I just push the top to the 181. Okay, I have another exercise for you. Well, it is a mini course, right? Maybe I can draw a picture. So we have this number, this function. So you have this g1, and then you can consider this map to this equation, or less like that. Sorry. And then we'll be arriving on domain by 5. Okay. And then we have a special component here, which is the boundary of the domain. So this is omega, okay, or this guy here. And we need the normal here. This normal here corresponds to a normal here, which is easy to compute because it is a graph. And then we pull back and it becomes another normal here with respect to the pullback metric here. It is not, it's not just DDT, DDS. And so, yes, so that denotes by G. We are still discussing about notation. So this guy will be the metric here, okay, which is so. And well, I can put here this guy, for example. This is the pullback by 5. Okay. And then we will denote by this guy the unit normal along this boundary, which is 1. Okay, with respect to and the point is the map is explicitly here. The normal is quite simple because of the normal of a graph, and you can use that to another exercise. Okay. This is very important. So this is G R plus Y. Okay. I mean, the map, again, the map is a split, you can compute the derivatives and get the. Look, we are looking for function phi such that the perturbation domain solves the problem, okay? And it's natural to consider perturbation that keeps the volume constant, right? So it means in this setting, we are considering, and this is the operators again, okay? Consider this guy here. The space we are considering is it's a 0 here to take functions whose integral is 0. Okay, so the functions. This is a closed manifold. Okay, it's not supportable, compact support. It's just to say that the integral Okay. And then try to put in the, yes,
This condition, in almost all the papers about interpretation is because you want to have the kernel of the linearity operator that has dimension 1.
okay.
Is it the same?
Well,
I mean, it's a technical condition sometimes, no? Because if not, you can have more by condition.
I don't know if I can show today, but yeah, we try to compute the linear Z operator and can show that, I mean, it is a symmetric operator. And using this condition, we can avoid the first eigenvalue. Okay. Well, I think it's a good point to stop.
Yeah.
Sorry.
No, it's okay, it's perfect. Maybe.
No?
No, okay, thank you, Marcos.
Thank you. Is that aí?
No, no,